Swayam Prabha. Digital India. Educated India.
Welcome back, and let's continue to the discussion of the ignition analysis of premixed flame. So, we are doing some simplified ignition analysis, and this we already discussed. What we are wanted to look at: minimum ignition energy, these are the application area, and these are the analysis that how we are going to do, because basically we will define a gas radius and then use the spark to find out that. So, this is the radius, that the gas volume radius, and here we will put the spark, and this is the critical radius, and that would be the burn temperature because of the heat production. So, we can actually correlate the generation of the from the energy equation, the heat generation to the heat conduction. So, that means we are equating the heat generated due to reaction and the rate of heat loss to the cold gas by conduction. So, these are the equation that you get then. Basically, it is a total amount of energy. Now, this we can replace by our previously obtained reaction rate delta AC 4 pi critical by 3 minus kappa 4 pi square dt by dr r critical. So, here dt by dr critical can be obtained from the temperature distribution, and r will lie between infinity and r critical. Then the temperature distribution, one can write this dt by dr at r critical is nothing but Tb minus Tu by r critical. Now, we substitute this 6.42 in 6.41, we get. So, putting 6.42 into 6.41, we get r critical square equals to 3k Tb minus Tu by this delta Hc. Now, we have already got some relationship in 620, 6.20, the average reaction rate in terms of. So, that already gives my average reaction rate in terms of SL and delta. So, that thing we can use, and also we have enthalpy of combustion is nu plus 1 Cp Tb minus Tu. So, 6.43 becomes R critical equals to root 6 alpha by SL. So, you get an critical radius, and here alpha is k by rho Cp. Now, if you replace these things with delta, one can rewrite this is equals to root 6 by 2 delta. So, that is another way to represent the whole thing. Now, one can note here that this factor root 6 by 2 is just an order of magnitude and should not be taken as a precise constant. Therefore, the critical radius is slightly or few times larger than the flame thickness. Now, we assuming the energy added by the spark hits the critical volume of the burn gas temperature. So, we can estimate that the ignition energy is M critical Cp Tb minus Tu, that is the ignition. And what about M critical? That is nothing but rho b 4 pi R critical by 3. So, if you put this back, you can write this is somewhere 61.6 rho b Cp Tb minus Tu alpha by SL cube. So, that is one way to express these things, which will become a function of burn density and the temperature and the flame speed. Now, one can eliminate this rho b from here by using the ideal gas law. If we do that, this so using ideal gas law, one can eliminate that rho b and you get E is equals to 61.6 P Cp by Rb Tb minus Tu by Tb alpha by SL cube. So, that is what you get. So, this is my ignition, these things. Now, we can get the pressure and temperature dependencies. So, from 6.47 we can assess the pressure dependency on ignition energy. So, what we get that alpha is proportional to Tu T bar 0.75. This is what we already obtained in 6.27. This correspond to 6.27 and also 6.29 has given us for N2 SL equals to T bar 0.375 Tu minus N by 2 exponential P to the power n minus 2 by 2. So, this is what we have already obtained in 6.29. So, these two information we have and we want to use this and connect with this ignition energy equation, and if we do that, what the combined effect of SL is E ignition is proportional to P to the power minus 2. So, this actually agrees quite well with the experimental observation. This has been already proven fact. Now, if T unburned is increased, then what happens to the impact? Ignition energy also decreases, because ignition energy is proportional to T unburned to the power some negative power of. So, these are my 6.48 equation number. So, that is how it depends on pressure and temperature. So, pressure and temperature. Now, this is how one can do a simplified analysis for ignition energy and get that. Now, we will move to the last important point of premixed flame is the flame stabilization. Why we talk about flame stabilization? Because this is very specific and one of the important issue for premixed flame, because we have already seen how premixed flame is susceptible to some issues like extension, flashback, lift off, and as we say, this is quite necessary to understand the flame stabilization to avoid flashback or lift off, because these are something which fits to the design of your reacting system. Because one hand, as we have seen earlier or kept on discussing this, the premixed mixture or premixed reaction system has less impact on the emission and the pollution, but at the same time this is quite challenging to have a controlled combustion in premixed system. The reason is very simple, because your fuel and air, they are already mixed before they are getting into a combustion chamber or the reacting system. So, this is the major source of concern, because once you have a premixed mixture which is always sort of exposed to the reaction, so any transfer from the other side, heat source or in terms of radicals or anything, that can ignite this mixture instantly, and that is why one of the things that you see in your SI engine, the auto ignition, because that is a spontaneous ignition of this mixture, that we will touch upon when we will go little bit and talk about of the engines. Now, in flashback, flame actually enters and propagates through the burner upstream without the quenching. So, this is what we have already seen. That means, this is my chamber and the flame actually goes there and sit there, which will make damage to those system. And in lift off, flame is not attached to the burner, but stabilized at a distance from it. So, that means what happens? This is my system. If this is the burner, it is supposed to stabilize here, but due to lift off, it will stabilize like this. So, flame will be sitting somewhere else, which is also not good for the design purposes, because the heat will be generated and hitting this portion of the chamber and all this. So, there are lot of design issues. So, flashback has safety hazard, lift off has related to incomplete burning, ignition problem, control of the flame position. This would be some issues that would happen. Now, one can see these are some schematic of a lab scale burner, where there is a mixture comes through this and this is the flame front. So, this is the flow comes in, this is the burner and this is the flame front. If it is theoretically nice organized flame structure, it is supposed to be stabilized right there, but if it is lifted, the flame would be somewhere sitting here, or if there is a flashback, the flame would be somewhere sitting inside like this. Now, more to it, both of these phenomena, the flashback and lift off, are related to matching the local flame speed to the local flow velocity. So, that is quite important when one wants to avoid this. So, the flame can only be stabilized on the burner for certain flow velocity limits. That means, this will be attached to this burner for certain condition. If I push or if I inject with too high velocity, the flame would be pushed back. So, for a defined or controlled limit, this flame would be only stabilized at the burner, otherwise either it would be pushed back or it may come up. So, both of these situations are likelihood possibilities. So, third is that if the gas velocity is progressively reduced, a point will be reached eventually at which the burning velocity exceeds the gas velocity somewhere across the burner, and this is where the flashback occurs. That means the upstream velocity, see the burning velocity will be occurring towards this side normal to the flame front. Now, if this gas velocity reduces and some point of time SL becomes higher, and then the flame would start propagating upstream. So, this would happen and that will lead to the flashback. So, if you put some, this is again a representative picture. So, this is an fuel oxygen ratio within the increasing side, this is the flow velocity, and there is a different zone what you can see. One is this small zone sitting there is the flashback. This is again a unwanted phenomena. So, one has to design the operating conditions and the system such that flashback does not happen. This is flame blow up, that means it is completely blown up out of the system, which is also not a desired system. Then this is the stabilized flame, what we mean by burner flame, burner stabilized flame. This area is something burner or stabilized or lifted flame. Then there would be again a limit of blowout with the lifted flame. See, the lifted flame has an issue that if you push these things too much, like if the flame front pushes here slowly, I mean it is lifted and then it can go out of the beyond the chamber. So, it will happen, and this side is your extinction side because the flow will be completely extinguished. So, there are certain limits which these things put you, and your design should be constrained to this parameter so that you have. So, that is pretty much that we wanted to discuss about the laminar premix flame, and we continue now on our discussion in the non-premixed flame. Now, once we do that, then slowly we will get into the turbulence and the turbulence non-premixed system, because when you go to the turbulent system, all this understanding of flame speed, flame thickness, ignition, flammability limit, blow up, and all this would be a required information one has to understand. Now, when you say non-premixed, which clearly makes a difference between your premixed system and non-premixed system. What happened in your premixed system? The fuel and air, they are mixed and then they are pushed to the combustion chamber, and in a non-premixed system, if this is your combustion chamber, fuel and air, they are injected separately, and the mixing takes place due to molecular diffusion inside the chamber before the ignition takes place. So, it clearly a difference, but it gives you some flexibility, but obviously when you talk about this, the non-premixed flame, they are more or rather well known for producing lot of emission, like emission gases, soot and all these. They are also quite easy to handle, or rather they are stable, but you pay the price in other factors. So, it is an again all the time this is a process of optimization. So, one hand premixed system gives you some advantages, but that also come with some concern. Non-premixed system can avoid those concern or can be free from those concern, but it will give you some other issues to control. So, bottom line is that all the time it requires the optimization of the system, and then how well it can be used for the purpose. Now, What we know, for a diffusion flame, the combustion occurs at the interface between the fuel gas and the oxidant gas, and the burning depends more on rate of diffusion of reactant than on the rate of chemical process involved. So, it is always in the interface where fuel and oxidizer they will interact, that is where the reaction takes place. So, it is more difficult to give a general treatment of diffusion flame, largely because no simple measurable parameter analogous to the burning velocities in premixed flame can be defined. So, that burning velocity that we defined in the premixed flame, that is actually not a parameter which you can define for a diffusion flame, because the whole idea behind premixed and non-premixed, they are different. As soon as you go to non-premixed, this definition of burning velocity does not exist. You cannot actually define it. Now, application wise, obviously the non-premixed flame, the application would be more, and it is starting from your residential gas application, but though that is a slightly partially premixed flame, you can have in a plenty of places where it is used, and we have already seen that. So, it can be used in fundamental research. So, one of the concern is that how you can control the flame shape. You can control through fuel flow rate, you can control through fuel type, you can also control through other factors. So, if you look at this example of this simple candle flame which we have seen earlier also, it is a very nice flame, but which we use in our daily life without knowing that actually burns under non-premixed mode. Now, here this is the solid candle which is a carbon, and you have air which is coming through, and the solid carbon actually through pyrolysis it reaches a gaseous state. This is your pyrolysis process, and the reaction takes place. So, there are different zone what you can actually distinguish. This is your main reaction zone, and this is your luminous zone which you can see there. When the candle burns, you can see a nice luminous zone there is there, and this is some of the other reaction zones where you see some radicals, CH zone, C2 zone there. Now, if you ever dare to put your fingertip through this candle flame, you will see the maximum heat at the outer surface. When you come close to the inner surface, you can see there will be minimum heat there. So, that will not affect, but obviously, I mean the other way to measure it, that you can use some thermocouple, which is a temperature measuring device. So, if you use a thermocouple and put it inside, you can see the temperature variation there, and that tells you in a different zone how things actually vary. Now, this is a typical diffusion flame structure. This is my flame front, this is also flame front, this is my fuel, and this is the oxygen. So, fuel comes down, also oxygen is completely consumed at this location. So, one can see that products is forming here, that is the peak, this is the product line, oxygen will be completely consumed, fuel would be completely consumed, and in between the center line fuel is varying, product is also varying, and oxygen is also varying. So, the nitrogen variation is also shown there. So, typically if you see, this is what happens, basically these are the areas what we kind of see there. These are the points, because this is one area reaction zone, this is another area. In the reaction zone only you get the products out of that. Now, you can have different diffusion flame regime, and this is based on the, so this is the flame height along this. So, first thing you can have laminar diffusion flame, and you can see in the laminar diffusion flame with the increasing jet velocity, that means for a simple jet flames, this is not for all, this is for some jet flames. You can see the height, it is increasing, that is a laminar diffusion flame. Now, this is along with the increasing jet velocity. So, that means when you increase the jet velocity, it reaches at certain point where beyond increasing the velocity, you may have a different kind of flame, which is not, see this structure, if you look, these are nice looking structure, but beyond a certain point the structure gets into this kind of structure, which are not nice looking structure. So, this is called that. So, this division is based on your fluid mechanics. Laminar, very calm, quiet situation, things are nicely balanced, you get to see nice flame structure. You increase velocity to a beyond limit, you get to see this transition zone, where the flame structure become quite chaotic, and there would be envelope of breakup point, there will be envelope of the flame length, and if you increase further, you are in completely turbulent zone. So, that means it is a pure chaotic structure of the flame front, and there is a nice analogy you can extract from this picture, is that this is exactly what we are doing. We are first we started, I mean before that, if I put something, these are the basics or fundamentals. So, this is where we discussed about all the combustion fundamentals, basic thermodynamics, kinetics, heat and mass transfer, coupling of kinetics, everything. Then we got to laminar system, then we want to go to turbulent system. This is exactly what you can correlate from this picture, where starting there is a laminar nice looking structure. These are certain properties what one has to understand, and why the laminar goes into transition with the increasing velocity. Then you see the flame structure is distorted, but it is not completely chaotic. But when you become completely turbulent, it becomes completely chaotic. So, that is why we started here and slowly go there, because whenever we look at this turbulent system, you require the information of this laminar understanding, and that is what we are doing, and we will stop here today and continue the discussion in the next lecture. Thank you.